Swami, can you hear me?
Yeah, Prasad, you can go ahead. I've already made it.
You already made. Okay, fine. So firstly, let me introduce the speaker actually.
That is the problem.
1 minute. So good evening. Good evening to all the esteemed members of the Ocean Society of India, ladies and gentlemen. We know that the Ocean Society of India regularly conducts invited talk as a part of the OSI webinar series, which is held once in every month. And this talk is arranged from eminent scientists, engineers, academic professionals working in the broad areas of atmospheric and ocean sciences, ocean engineering and technology, and allied areas. So this webinar is mainly targeted for the students, the researchers, scientists, engineers, and working professionals in the field of atmospheric sciences, ocean engineering, and technology disciplines. So the motive behind this webinar is to impart and improve the knowledge that benefits the community. So I request all the members to actively participate and get involved in all the lectures that is held under the OSA webinar series. So on behalf of the Ocean Society of India, it is my proud privilege today to welcome Dr. Nagaraju Chilukoti, Assistant Professor at National Institute of Technology, Rourkela, for the invited talk. So Professor Nagaraju will be delivering a talk on the topic, A Curious Case of the Indian Summer Monsoon 2020, the influence of Barotropic Rossby Waves and monsoon depressions, which is a topic of relevance for the meteorologists, oceanographers, and allied disciplines. So now let me give a brief background about Professor Nagaraju. He obtained his bachelor's degree in mathematics and physics from Acharya Nagaraju University and master's degree in meteorology with a distinction from Andhra University, Visakhapatnam. He obtained his PhD in atmospheric sciences from the Indian Institute of Tropical Meteorology, Pune. And Professor Nagaraju is a very serious researcher and dedicated scientist, having exemplary track record in research and publications in high impact peer-reviewed journals. And I was going through his CV. He has actually research interest on wide topics, varieties of topics. He works on the coupling of simple biosphere model with NCEP CFS model, implementation of varying vegetation map as part of the land use land cover changes in CFS model, the coupling of the ocean model ROMS with the regional atmospheric model WRF to predict the Indian summer monsoon, and study the impact of anthropogenic emissions on the regional climate, study on changing tropical Indo-Pacific climate drivers and its impact on the Indo-Australian monsoon links. Then on statistical and dynamical downscaling techniques to improve the seasonal monsoon prediction for India. He's also involved in development of real-time weather system at CDAC for village level forecast. So after completing his PhD from IITM Pune, Professor Nagaraju worked as a research fellow at IITM to understand the Asian monsoon, its variability on different time scale using the CFS V2 model, the decadal variability of Indo-Pacific climate drivers and its impact on Indian summer monsoon rainfall, the decadal changes in the relationship between Indian and Australian monsoon, the potential influence of Atlantic multi-decadal oscillations on ENSO. So thereafter, he worked as a project engineer at CDAC Pune from December to May 2013. He was involved in porting the WRF ROMS, the MOM model, GFS for operational regional forecast, monsoon forecast, and coupling of WRF with ROMS using script, and many other areas he was involved in. And from June 2013 to March 2016, he worked as a scientist at INCOIS Hyderabad where he was involved in the validation of ocean state forecast with all available in situ observations, the bias correction during synoptic weather disturbance, the setting up of the real-time WRF Mike model, WRF SWAN model for the ocean state forecast, and many other activities also he was involved in. And from March 2016 till March 2018, he worked as a postdoctoral researcher at the University of California, Los Angeles, USA, where he was involved in coupling the simplified simple biosphere model with NCEP CFS model and implementation of varying vegetation map in GFS and CFS. He also worked as a scientist at IIT Bombay from May 2018 till January 2019. He was a visiting research professor at Yonsei University, Seoul in South Korea from January 2019 till March 2020, where he was involved in working on the tropical climate dynamics, the variability of the Madden-Julian oscillation during mid-Holocene and its impact, the Atlantic multi-decadal oscillation, etc. Then he joined as an assistant professor at NIT Rourkela in March 2020 and presently is continuing in the same institute. He is very actively involved in the research on the Madden-Julian oscillation variability during the Pliocene and the mid-Holocene periods, and also on the data assimilation techniques. So Professor Nagaraju is a life member of the Indian Meteorological Society, the Ocean Society of India, the Korean Meteorological Society, and also member of the American Geophysical Union. He has published actually several peer-reviewed papers in reputed national and international journals. With this brief introduction, it is my proud privilege to kindly invite our speaker for today, Dr. Nagaraju, to deliver the talk.
Yeah,
so it's also requested that the questions and answer session can be attended after completing the talk, and this can be messaged for the speaker in the chat box. Thank you.
Yeah, thank you, Professor Bhaskaran, for a nice introduction. So
yeah. So I will just put it in the full screen mode. You can just tell me when to go forward actually.
Yeah, sure.
Okay.
But slides are not visible, sir. There's a blank screen is visible to me.
1 minute, let me.
Yes, now it is visible. Yeah, but your voice is not there. Hello? Am I audible, sir? Your voice is not coming, sir, actually. I think you are muted.
You have to speak, Raju. You have to speak. You can carry on.
Yeah, can you put in a full screen mode, sir?
That is from your side.
That okay, yes, given. No, the slides are operated by this Professor Bhaskaran because
Okay,
I am unable to share. So my system is not
bring
allowing
into
some.
slideshow. Prasad?
I think I can operate from my side.
So now can you hear me?
Yeah, yes, sir.
Okay, fine. So I'm making it in the full screen mode now.
Okay, sir.
You can just see whether it is able. You're able to see the slides.
So I can move forward and back my slides. Is it possible to move from my side?
No. I have to move it from here.
Okay, sir. Yeah, maybe first slide I can.
So the first slide is this one. Yeah.
Yes, sir. Yeah, thank you, sir. So good evening, all. So thank you, Professor Bhaskaran, for giving this opportunity, and I'd like to thank all the Ocean Society of members for giving this opportunity. So today I'm going to talk about this a curious case of the Indian summer monsoon 2020. So this is a very peculiar monsoon year. So in this year we have received a very high amount of rainfall during August. So before going to talk about this thing, so I will talk about some basics how the Indian and other climate drivers, so ENSO and IOD, how it is running. So I would like to thank my student Mahendra so for his contribution, and I would like to thank also Dr. J.S. Chowdhury from IITM Pune, who is contributing along with me for this lecture. So basically, I am talking about this monsoon. What is monsoon, and what are the basic factors influencing this monsoon, such as ENSO, IOD, and other climate drivers. So, and what are the changes in the recent in the teleconnections? So, how they are influencing and how they are decadally varying from one decade to another decade. And I will focus on the my talk on the case of 2020 monsoon. It's a very peculiar monsoon, and I will summarize. Sir, can you go to the next slide?
Yes.
Thank you. So before going to talk about this curious case of the monsoon, so what is monsoon? So we all know the monsoon is a seasonal reverse of winds, which is associated with this torrential rainfall. So in one season, winds will come from the southwest, and another season it will come from northeast. So this is the completely 180-degree reversal of the winds will be there. So which is accompanied with the torrential rainfall, which will bring this to the Indian region. So because of this seasonal variation of this solar radiation, so which will bring this temperature gradients in this Indian region, and which will uh, generate this pressure gradient, and pressure gradient changes the circulation pattern, so which will ultimately give the rainfall. So this Tibetan plateau act as a elevated heat pump, so which will bring this moisture to this Indian continent. So and recent study by this Jin et al has showed that one along with this Tibetan plateau. So there is a mineral dust which is coming from this Sahara and these other dry regions, so which are contributing and acting as a elevated heat source, so which is intensifying the monsoon. So that's what I'm not going to talk. Just this is the recent changes in the monsoon connections. So sir, next slide. Yeah, basically this monsoon. So when this was documented scientifically by this Edmund Halley in the year 1686. So what is causes the monsoon? So because like every year we are receiving a torrential rainfall and the seasonal reverse of the wind. So in the Edmund Halley in the 1686 in his paper, so he documented what causes the changes. So his paper you can see in a historical account of the trade wind and monsoon observable in the sea between near the tropics with the attempt of assign the physical causes of the winds. So he is trying to explain so why these seasonal rivers of the wind and why these rainfalls are there in the seasonal. So he's trying to explain the using the seasonal. So according to his theory, so first he has proposed so the temperature, this specific heat capacity of this land and ocean is different. So this will create the land ocean temperature contrast, that is the temperature gradient will created by this variation in the seasonal variation of the solar radiation, so which will bring this changes this pressure patterns, and this will brings the torrential rainfall to the Indian region. So like this he is documented. So he is the first man to scientifically documented this the theory of the monsoon. Next slide. So before going to this one, so what are the physical driving mechanisms for the monsoon? So basically, if you see this monsoon, so then when he has proposed this only land is temperature contrast. So this is not only the sufficient condition to explain. So because once the monsoon onset has happening, it is spread all over the India, the temperature contrast significantly reduces between the land and ocean. So then how it is maintaining? So you can see there's a significant driving mechanisms. There is differential heating and the land ocean, what Edmund Halley has proposed. So other than that one, so moisture process, the release of this, because in the seasonal variation of this solar radiation, so these oceans get heated and evaporated, water is evaporated from the ocean and which will transport to the land. so which will release the latent heat, right? Heat transport to the Indian region. So like this, and rotation of the rotation of the earth, because that is a Coriolis force. Because when the monsoon has started from this Madagascar, which is in the southern hemisphere, so which will then winds, then low pressure over the Indian region, heat low. So then winds are not coming straight way. So they are coming the cross equatorial flow, and initially they start as a southerly wind. Then it will modify by the Coriolis force. It will turn into the southwesterly winds. The similarly in the winter monsoon. So we have two monsoons. One is the southwest monsoon, this is the summer monsoon, and another is the northeast monsoon, that is also called as a winter monsoon. So these seasonal reverse of this solar radiation. So the seasonal changes in the solar radiation, which is appeared as a land sea breeze. You can see this is the daytime. If you see the land sea breeze theory, what it will say, daytime the ocean will be relatively cooler and the land will be very get heated. The low pressure will form. Then from the winds from the ocean to land it will come. So similar way in the monsoon case also, in the summer time, what will be Indian region, this heat low, the northwest region and Pakistan region will get a very warm, and there is a low pressure will form, and because of this cooler region in the Madagascar region, so that will act as a high pressure, there will be a high pressure area. So like this, so has explained, so the land sea breeze contrast how it is more. So like this, this monsoon is initiating in so next slide. So after because this is the initiation and the first step, land ocean contrast. But after this land ocean contrast, what will happen is the land ocean temperature contrast will significantly decrease because of the cooling of this land surface. So our processes will drive the mechanisms. You can see these the rainfall patterns which will show there in the summer and winter. So you can see this is the winter monsoon. This is a January and February rainfall. So this is global rainfall. So January and February, the Australia and the maritime continent and the south of Indian Ocean, southern Indian Ocean regions. So these regions will get a rainfall because of this region is a summer for them, southern hemisphere summer. So this region will get a rainfall. In the Indian case, so during the July and August, the JJ season, so India receives the most of the rainfall during the time. You can see this high amount of rainfall in the Indian region during the July and August. This is the picture shows the July and August and January and February, not JJ season. So what causes this? Because why this land and temperature contrast? Because the land is a specific heat capacities compared to the ocean, the water, so is low. That is the one reason. Another reason, so in the ocean, when get heated, so due to the turbulence mixing, so it will get turbulent mixing, and it will take time to heat up this upper layer of the ocean, because it is a turbulent mixing continuously few meters it can penetrate. But in the case of land, that whatever the solar radiation is coming, it can heat up to few centimeters only. But in the case of the ocean, it will can heat up the up to few meters. So because of this penetration of this solar radiation. But in the land case, what will happen? The poor molecular, slow molecular heat transfer, it will take place. So it will get heated, and heat capacity will very low, and then heat capacity is very high in the water, and heat capacity is very low in the land. So this will create a differential heating in the land and ocean. So which will bring this initially the temperature contrast, and this will bring this pressure gradient, and the pressure gradient changes the circulation. These circulation changes will carry the moisture to this river, to the India. Next slide. So we have seen that after the onset of the monsoon and monsoon march spread over this all India, so what will happen? The temperatures will be come down, right? So what maintains the this monsoon circulation? So in the main process, another major process is the moisture process, because this water evaporated from the sea oceans, so which will bring the to the land, and it will condensation. It will release the latent heat over the Indian region. So it will act as a heat pump, so or solar collector. So this will create the temperature. This will maintain this temperature gradient between this ocean and land. So this will maintain the circulation. So this moisture land, if it is a moisture is present, it will act like as a ocean. If this land is dry, and rising motion will occur, and closer to the coast, since the land will be very warm, so this very warm, so this is very dry, and then it will move as land becomes wet, and from the precipitation, the rising motion will move inland over the dry land. So when this onset is happening, that a very dry land, so then it will get cooler, and then the other remaining part of the dry land, so then slowly it will shift, and it will slowly progress to the entire country. So like this is the one way to the progress the march. And another thing to maintain the circulation, also latent heat whatsoever releasing because of the condensation, so which will act as a elevated heat sources along with this Tibetan plateau elevated heat source. So this will maintain this monsoonal flow to enter the season. So next slide. So far we have seen the what is the process of, and I forgot to mention that the orography. So orography also, if you see the spatial variability of this monsoon rainfall. So the Western Ghats region and Northeast region, and these regions will get a very high amount of rainfall because of this orography. So we have seen that moisture, land, differential heating of the land and ocean, and this moisture process, and the Coriolis force. So these, apart from this, and orography also significantly contributes the monsoon rainfall, because the most of the rainfall during the Western Ghats and this Northeast region. So because of this process will dominate, orography will orographic lifting is dominant. So that's why these regions will get a very high amount of rainfall. So in the case of the Tamil Nadu, so what will happen because of this moisture it is losing after crossing this Western Ghats, so it will descend the descending this monsoonal flow, and it will it's a dry region over the Tamil Nadu region. That's why we call it as a rain shadow region. So to explain this monsoon, there are some theories available. So who started first? Edmund Halley has proposed a monsoon as a gigantic land sea breeze because of the land ocean contrast. So it is initiating, and what is the objection for this theories? Because it is a main objection for it is this theory. So during the May time, India get most land sea contrast. Right, May is a very hot season, so land gets very much hotter. So ocean is relatively cool. So then this time we are not getting any rainfall, and that to Northwest region and Pakistan region will be very receiving a very less rainfall. So because the temperature contrast, if you see the land and ocean, so this region and the ocean and this Northwest region will have a temperature contrast, but it is not the case. So and spatial variability also is unable to explain this land sea breeze theory. So then Hadley in 1735 slightly modified. So he has added the Coriolis force into the this theory, and he has tried to explain, but it is not fully explained. So after that one, Simpson, so in 1926, Simpson so objected. So monsoon is not a land sea breeze theory. So he explained because of this configuration of the various these mountains, so it will act as a like if you take this northern side, the Himalayas and Tibetan Plateau and these northeastern mountains, it will act as a barriers, like which will not allow the monsoon flow to go. So they will force this monsoon wind to rise, and which will give the rainfall. So like this he has explained, and some theories also is available. They have the Sikka and Sulochana Godgill. So they have also studied. So this is a, they thought that the seasonal variation of this solar radiation and these things will responsible for the manifestation of the seasonal Indian summer monsoon. So like this, many theories are available in the literature. So can you go to next slide? So as I told, like a Simpson, you can see this is the topography of this India. So you can see these regions will act as a walls. So which will the monsoon time we are getting a southwest flow. So which is not there is no way to escape from this region. So it has to rise. So like this, he has explained the highest rainfall in the Western Ghats and Northeast region based on the this orography effect. So this region is getting most rainfall, and this region, Tamil Nadu region, getting a very less rainfall, and this northwest region is not getting rainfall because of this monsoon flow, which is coming. Which is coming from this Western Bay of Bengal, not from the Arabian Sea. So one flow will come like this, and it will from the head Bay of Bengal to the towards the Pakistan, it will extend. So because while going to from head Bay of Bengal to the Pakistan region, so most of this monsoon flow lose the moisture, and when it reaches the northwest India and Pakistan region, it will receive a very less amount of rainfall. Like this, he has tried to explain the spatial variability of the monsoon rainfall. So next slide. Yeah, like this. So he has showed that one. This is a red line. It is like a, if you think it is a box. So two sides are closed and the two sides are open. The winds will enter in this side, and it will not no way to escape from this region, and it has to rise. So that is the rising motion. So this will ultimately give the rainfall over India. Next slide, sir. So we have seen during the monsoon time. So there is a monsoonal. We are familiar with southwest monsoon time. So there is a southwest flow will be there. So which will bring this moisture to the Indian land, and the northeast time. So we'll get it during the winter time. So we have northeast winds, which is coming from the Siberian high. So which will bring the most of the rainfall to the South Andhra Pradesh and Tamil Nadu coast. So these regions will get it most of the rainfall in the winter time. So during the summer time, this region, this Tamil Nadu region is very dry. So which receives a very less amount of rainfall. Next slide. So during that time, so how the circulations will be there. So far we have seen that only is the surface. So you can see the subtropical jet. So this is the high, this is the winds at streamlines at 200 millibars level. So you can see this in the January, so there will be a subtropical jet near to the 30 degrees north. So when this monsoon is onset, this subtropical jet will shift towards the north, and the high pressure over this is upper level divergence. So you can see this is over the Tibetan Plateau and this Indian region. So it is a strong anticyclone will be there. So because of this anticyclone, so the tropical easterly jet, it is a very peculiar to the Indian region only. So you can see from the South China Sea to the up to the coast of Africa, only it will be present. So whereas this subtropical jet is the encircles the globe. So tropical easterly jet present over the only Indian region. So these are the typical circulations during the monsoon time. So you can see only in Indian region. Next slide. So there are theory, like we have seen the land sea breeze and the mountain configuration is producing rainfall. Another theory, and so many these other scientists, renowned scientists, also believe that one monsoon is a manifestation of the ITC jet. So after that one, so they found that one, so ITC jet, CTC, continental tropical convergence zone. So like this, so you can see what is the basic difference between this ITC jet and monsoon trough. So monsoon trough winds will be converged from the northeast trade winds and the monsoonal winds, which are coming from the this Madagascar high. Whereas this is the ITC jet. So both northeast trade winds and southeast trade winds will merge, and it will give the rainfall. So this is the ITC case. This is a monsoon trough, so which is different. So because it's not intertropical convergence zone, so that's we call it as a continental tropical convergence zone, or this is different. Like this, somebody will thought that it is a part of the ITCJ manifestation of this monsoon. So that Murakami has objected. So because if you see this variation of the ITC jet movement from the season to season, so very large variation, nearly 40 degrees latitude variations will be there over Indian region, and because these type of large changes you cannot find in other regions. Mostly it will be 5 degrees north to 5 degrees 10. Only it will vary. So whereas the Indian region it will vary up to 40 degrees north. Also it can vary. Yes, next slide. So what happens like during the monsoon time? So what will happen is the rising these winds will come from this high pressure Madagascar to the Indian region, so which will give the rainfall over this region, and which will another branch, the rising branch, so which is again it will sinking motion will be there over the Madagascar. You can say rising branch over the Indian region. So this branch, so rising, and the sinking motion will be in the dry and over the Madagascar and southern latitudes. Yeah, next slide. So far we have seen that what is the theories. Like I have given a very brief introduction. So what are the theories available? What is the causes or drives the monsoons? So why this intra-annual variability of the monsoon, right? So we have seen that every year we are not getting a similar amount of rainfall, and year-to-year variations are there. So what drives the this monsoon? So one of the important driver is ENSO, Illinois and Southern Oscillation, which is a the air air-sea interactions. So these are two components. Oceanic component is this El Nino, and atmospheric component is Southern Oscillations. This is called El Nino Southern Oscillations. So these air-sea interactions in the Pacific Ocean. This is a teleconnections, not in the India. So these teleconnections, these ENSO and Southern Oscillation impact in this Indian rainfall. They found this relation between the ENSO and Indian monsoon rainfall. So ENSO has a three phases. One is the neutral phase. So and what is the normal conditions? So normal condition means like Eastern Pacific is cooler and Western Pacific is warmer. So that Walker circulation will be there, and the rising motion over the Indian this maritime continent, and sinking motion is the Eastern Pacific region. In La Nina conditions, what will happen? So abnormally, the Eastern Pacific will warm, and the sinking motion will happen in the Western Pacific region and the maritime continent, which will oppose this Indian monsoon circulation. So that's why Indian monsoon will be weakened. So this is well-known phenomena. The La Nina case, what will happen? Normal condition will intensify. So that means like more cooling will happen in the Eastern Pacific, and more warming will be there in the Western Pacific. So these changes will alter the or modulate this Indian summer monsoon rainfall. So how it will connect this Indian summer monsoon? Through the Walker circulation. Through the circulation, so changes in this east and west temperature anomalies will alter this Walker circulation. This Walker circulation modulates the Indian summer monsoon rainfall. Next slide. So this ENSO impact, so not only the Indian region, so worldwide it will impact. So this figure shows the during the ENSO time. So these regions will be yellow color will be dry, and these regions will be wet. So you can see these are during the El Nino time. So this region will get the green color. So in the Pacific and Central Pacific and Eastern Pacific region will get a very high amount of rainfall. That's why wet. And the Indian region will be dry, mainly dry, except southern tip, and the West Africa, this coast, and some regions in the other countries. So this is the global effect. So that's why we call it as a teleconnections. So some regions will get a high amount of rainfall, and some regions will get a very dry region, so very breaks and prolonged droughts. So basically, India and ENSO relation. So during the El Nino time, India receives a very less amount of rainfall. This is the well-known phenomenon. Next, please. So what will happen during the El Nino time? How it will change the patterns? So you can see this figure shows this normal conditions. How the this time generally this winds will be from this southern along the coast of Peru, and which will cause the upwelling in this region, and it will be relatively cooler, because upwelling will bring the cold water from the subsurface to the surface. So that's why it is relatively cool. And these trade winds push the surface of warm waters towards the west. So that's why it is very warm, and relatively this is cool. This cooling will happen because of this coastal upwelling, and coastal upwelling this region, and this warming because of this surface warm water continuously pushed, that's why there is the elevation difference will also will be there. So this water is piled up here, so that's why the warm water will pile up here. The sinking motion will happen. This is the upwelling, and this downwelling will happen. So this this is the difference between. So slowly what will happen in the case of El Nino, the winds, these winds along the coast, Peru coast, winds will be weakened. So then the flow will be reversed, because this continuously forcing that we stop this wind stress. So what will happen, because this water will flow, this surface currents, and warm currents will come here, and this will be weakened, then it will stop the upwelling here. So that's why this region will be warm, and this relatively warm, and this convection shift during the El Nino time to the eastern Pacific. So these changes, thermocline also will changes. So during La Nina time, what will happen? This will be very strength. These winds are these trade winds are very strong. So then there is strong cooling in the thing, and the warming will be there in the Western Pacific. So this will, you can see the thermocline. This is a very deep thermocline will be there in the Western Pacific, and very shallow in the Eastern Pacific. Next slide. So because of these temperature changes, so this Walker circulations. So basically, I'm trying to connect how this how this ENSO is affecting the Indian monsoon. So normal years, so this ENSO during the normal year, the Eastern Pacific is colder and Western Pacific is warmer. Because of this warming, this low pressure will form, and the winds will converge here from the both sides, and it will raise the rising motion over this maritime continent and this north of Australia. So which will receive the most of the amount of rainfall. This is a normal condition. In the El Nino year, what will happen? So these conditions will be reversed. So relatively, this Eastern Pacific is warmer, so the convection shift to the East Pacific, and the Walker circulation will be. You can see that normally this is from the east to west. So, but in here winds will be reversed. The west to east it is blowing. So that circulation will be reversed in this El Nino condition. During the normal this strong La Nina condition or La Nina conditions, what will happen? This will be intensified circulation will be there. Next slide. Yeah, apart from this El Nino, so recently that Modoki, that is the central warming Pacific. So far we have seen east or west warming. So apart from this monsoons, so Modoki also central Pacific is warming. So in normal conditions, this western is warming, and in El Nino conditions, Eastern Pacific is warmer. But in this case, El Nino cases, central Pacific is warmer, and the both sides like east and west are relatively cooler. In the case of La Nina Modoki, that the central region of Pacific, tropical Pacific is relatively cooler, and the east and west will be cooler, and the convection will shift to this both sides. And in the El Nino Modoki case, the convection will be in this concentrated over the central Pacific. Next slide. So this is the, you can see how this changes. So because these are the normal conditions, so which is West Pacific, warm and rainy will be there. Then deep thermocline, you can see here because of this lot of vertical energy is available, that vertical mixing will happen. So that's why the thermocline will deepen here. So here this is relatively cooler, and this mixing will be very low, and this upwelling will happen. So that's why the thermocline is shallow in the East Pacific. Next slide. And is quite opposite in the La Nina case. What will happen? This El Nino case. So El Nino cases, what will happen? This East Pacific is warmer and relatively cooler. This is shallower thermocline in the Western Pacific, and the deeper thermocline in the Eastern Pacific. So winds will be reversed, and the convection will be shifted to the East Pacific. Next, please. So you can see this is the picture shows this how this Walker. This is so far we have seen the schematic diagrams. In the real case, how it will look like. In the real case, it will not be that much clear. You can see even though this is the composite of 11 El Nino cases, how the Walker circulation will look like. So this is the area average 5 degrees south to 5 degrees north of the 11 annulus which has occurred 1952 to 2002. So you can see this Walker circulation. So this is the warming. This background is shaded is SST. And the relatively this is Western Pacific is cooler and the Eastern Pacific is warmer. So that's why the rising motion you can see clearly. The rising motion will be in the Eastern Pacific and the sinking motion will be in the Indian region and this region. So you can see. So it is the other this is the composite of this is the zonal circulation. This is the meridional circulation. How it will be in the during El Nino cases. So there is a sinking motion will be there. So you can see this is the sinking motion in the Hadley cell. Also, Hadley cell. So Hadley cell will be this sinking motion will be there. So that is brings the dry condition over the Indian region. Next slide. So El Nino brings this drought conditions. We know that one Western Pacific rains and equatorial coast of South America and convective storms and hurricanes to the Central Pacific as majority droughts in India occurred during El Nino events. So this basin-wide warming in the Indian Ocean occurred during the El Nino. So recently we have found that once this is the when the correlate this El Nino is there, this Indian Ocean is there like a positive dipole, Indian Ocean dipole. So that this is another climate driver which is affecting. So this you can see this is the cooler and this is the warmer. This Arabian Sea and the southeast Indian Ocean will be relatively cooler. So this will be a dipole pattern in the Indian Ocean. So yeah, next slide. So similarly, that Pacific Ocean, we have seen that the variation of this SST anomalies. Similar cases in the last slide, what I shown. So Indian Ocean dipole. So similar type of like El Nino, the Indian Ocean also will have a dipole. So one that is the Indian Ocean dipole mode. So which is counteract this or counteract the El Nino conditions. Next slide, sir. So you can see this is the positive conditions. So basically positive IOD. So this is this region will be relatively cooler and this region will be warmer. So the convection, this white color, this shows the convection. So this convection promotes this Indian region and this region and this Africa region. So whereas the negative dipole mode case, so the convection shift to the Australia and maritime continent. So this is the similar to the ENSO. So it is in the Indian Ocean region. Next slide. So how it will evolve? So this is the evolution shows us how the IOD event. So in the May June, so there's slightly you can see the negative SST anomalies and slightly positive anomalies in the Arabian Sea. And if you go to the July, August, slightly intensified. So there's both regions and the wind anomalies also. And September and October, which is the peak season for this IOD. So there will be large strength will be there. So the winds will be from the high pressure this southeastern Indian Ocean to this Arabian Sea. So which will promote this circulation. So this is the positive IOD evaluation. In the case of negative IOD, it will be reversed and it will give the droughts. So when El Nino is there and positive IOD co-occurrence, it will nullify the effect of this ENSO. And if it is a ENSO, El Nino is there and negative IOD, then it will intensify this effect of drought. Very much drought will be there. So like this, there is a changes in the El Nino and ISMR relations, which modulates the IOD basically. Next slide. So how this IOD is maintaining? So once it is a warm and cold temperatures are persistent, so what will happen? This anomalous anticyclone, which will bring this surface cold water. So from the southern latitude, the pole latitudes, so which will bring this cold water towards this Sumatra and the coastal upwelling also will happen. So which will maintain this cold and these warm surface currents will accumulate like how this Western Pacific is accumulating the warm water. So like this, it will maintain the feedbacks. This is the positive feedback of this maintaining this positive IOD event. So like this, the wind circulations also will create a positive feedback to maintain the IOD. Next slide. So far, we have seen that El Nino, Modoki, how these are modulating. However, we have seen, see if you see the decadal variability of this monsoon, I think you can see. So this red color shows this departure or drought years, and this green color bar represents the excess Indian summer monsoon rainfall events, and this blue is the normal event. So you can see most of this drought years is associated with the El Nino. However, so 50% of this, nearly 50% of the cases is not associated with El Nino. So these cases you can see. So some of cases is not alone, but we are getting a drought conditions. Similarly, this La Nina, which is favorable for the Indian monsoon, which will bring this floods. But we have same kind of thing. So the most of the cases it is matching with the La Nina, and some cases it is without La Nina or any event. So we are getting a above rainfall. That means like that El Nino and IOD itself is not able to explain all the variability of the Indian summer monsoon. ENSO and IOD has a limited ability to explain this variability of the monsoon. So other than that one, so other forcing like by in our study we have found this Western North Pacific is playing a role apart from this ENSO and IOD. So it is playing a role in the modulation of the Indian summer monsoon. The next slide. So this is a study by this my student Mahendra. So he has studied so Indian summer rainfall. So we have seen so many studies also suggested that in recent years ENSO and Indian summer monsoon is weakening. This figure shows this spatial correlation between the Nino 3.4 and Indian rainfall ISMR correlation, and this is the area average 21 years sliding correlation between the Nino 3 and ISMR correlation. You can see some epochs, so it is weak. So this is the epoch 1 and epoch 4. This relation between this Nino and Indian summer monsoon is weak, and other cases it will be strong. So this below this dotted line strong, and therefore this one is weakening. So that's why this is recently it is weakening, and this epoch 1 also this is also is weakening. So this is 1979 words. No, sorry, this is from 19. I will show next lesson. Yeah, based on this one, so you can see the correlation has 19. So we have seen the previous slide. So correlation is recently is changing. Right, recently it is weakening and epoch 1 is strong. So how this it is overall we have seen the ISMR and Nino 3 correlation. If you see, go to the regional wise. So we have defined the 4 boxes. One is this this region black color, and another one is the red color in the central India, and this is blue color also, and this southern India. So there are 4 regions we have selected. 4 regions and we have selected 4 based on this correlations. So based on the correlation we have selected 4 epochs, epoch 1, epoch 2, epoch 3 and epoch 4. In epoch you can see seasonal variation of this relation between this ISMR and Nino 4. So some regions, so these 2 regions, the light blue and red color. So in the recent period and epoch 1 and the earlier period, so which are weakening. However, these other regions like this peninsular India and the northern Indian region, so these regions are very stronger. So these 2 boxes is very much stronger in the recent periods. You can see this overall. If you see the correlation over India, so recent period is weakening. But if you see the region wise, so regionally it is varying. Some regions it is getting very stronger, and some regions it is getting weaker. Next slide. So this is very interesting. So that's why we have studied. So further, this is how the Nino 3 and IOD correlations. You can see the Nino 3 and IOD correlations are decreasing trend, and whereas this Nino 3 Atlantic Nino correlations are also changing. So decade to decade. So where this epoch 1 and epoch 4 is strong, the correlation is epoch the Nino 3 and Atlantic Nino index. So another climate driver. So which is negatively strongly correlated. So whereas this ISMR and Nino 3.4 correlations, this below panel shows this in the epoch 1. There is ISMR and Atlantic Nino has a positive correlation. So where this weak correlation are there, and this during strong correlation where the ISMR and Nino 3 point correlation is strong, so these time negatively correlated. There is a decadal variation in this relation between these climate drivers. In some decades it's weak, and in some decades it is showing the positive correlation, and some decades it is showing the negative correlations. Like this, it is decadally varying. So why it is varying? So we'll see. Next slide. So one of the reason why these regional changes in the rainfall pattern. So one found, this is the figure shows the correlation between the Nino 3.4 and SSTs, which are significant at 90%. So you see, we have found a slightly westward shift of this extending this warm turn. You can see this warm anomalies. So this SST pattern is extending westward. So these in the epoch 1 and epoch 2 is very clear. So which are associating, you can see in the bar plot also we have seen the relation between this Nino and IOD is decreasing. So this can see in the epoch 1 so there is a strong IOD pattern. You can see the Nino, and coming to this recent period, so the correlation is weakening. So there is a decadal variation in the Nino and IOD also. There is decadal variation. So these changes are bringing this major changes in the rainfall regional patterns. Next slide. So why these regional patterns, like why this relation in during these epochs is regional rainfall pattern. So this is figure shows the precipitable water content during the epochs. You can see the intrusion of this from the western Pacific to Indian region, so in the head bay of Bengal. So the intrusion of this precipitable water content. So the positive anomalies here and here you can see, but it is not significant in the epoch 1 and epoch 2. So that's why this is a strong correlation during this period and weak correlation in this period because of this. Changes in this precipitable water content, so which is penetrating towards the Indian region, so which is causing the regional pattern changes. Next slide. So that's why we have done this, which is dominating and which is this not dominating. So we have done the correlation. So this is the IOD pattern. So correlation. Correlation Nino 3.4 with the streams and rotational winds. So it 850 hectopascals, removing this Nino 3, and this right panel, right 4 panels shows this removing the IOD effect. So a weak cyclonic circulation, these two epochs are corresponding to the upward motion over the head bay of Bengal. So you can see these two epochs. So there are upward motions, so which is promoting this rainfall over these regions. So because in the two epochs, which is causing the weakening of this ENSO and IOD relations. So that's what in these two regions, this in the recent period. So and the earlier period, epoch 1 and epoch 4, the El-Nino relation is weak during this period. Next. So why these two regions are weakening? So because we have observed that this anticyclone is extending during the these two epochs. So these west north Pacific anticyclone is extending, so which is promoting this changes in the circulation pattern over the Indian region, which is promoting the rainfall. So because of this extension of this west north Pacific anticyclone region, so is the main region for this excess rainfall over these regions, two regions. Next slide. So these relations, how these models are able to capture. So there we have verified in the semi-fixed models, but most of this we have for this verify the physical mechanism dynamics. We have selected 29 semi-fixed models. So then we have seen that most of the model is able to capture this pattern. So like the seasonal peak and all the things, but it is not able to capture the capture the magnitudes. You can see most of the models are underestimating this ISM or rainfall. Next. So then we have seen this how this standard deviation of NINO 3.4 anomalies as IOD and NINO indexes, how the models are predicted. So some of the model, nearly 75% models are predicting, but not exactly as the way. This panel, the observational A, the first left corner, top left corner. So this is the observation. So then most of the models are able to reasonably well, not bad. So some models are very bad. So they are not able to capture this variation in the SST anomalies in the NINO3 and IOD and NINO index. Next slide. So similarly, this correlation also, coefficients also we have found. So intermodal variability is very much high. So during the epoch, S means there is strong epochs with a strong correlation. W means weak correlation. Epoch, weak correlation epoch. So there are in the observations we have seen the epochs, the central Indian region, so which is weakening the relation between the NINO 3.4 and Indian monsoon correlation. Whereas this most of the models, so except few models, most of the models shows the correlation is continued as a negatively strong negative correlation. So this is not showing that central India weakening. So some models only is able to predict like this. MPI ESM and MIROC 6. These models somewhat has represented this variation in the correlations, so they are able to capture, but not very well. So, but reasonably capture the variations. Next slide. So similarly, this is also sliding correlations. How this between the models are able to capture this NINO 3 and JJS rainfall correlations. So most of these models are failed to capture this decadal variation in the NINO 3 and ENSO rainfall correlations. Yeah, next slide. So this is also verification of this IOD, NINO 3 variances. So how the observed variation and model variances. So however, these models are showing limited fidelity in predicting these type of variances. So that's this. This is reveals that one. So we have to improve the physical process representation. So because so if you see the ENSO and IOD is a dominating factors, so they are not able to explain and they are not able to predict this very well. So if you are not able to accurately represent this physical process and physical mechanisms, so that model will not be able to predict this accurate rainfall. The next slide. So, so far we have seen that how these decadal variations of this happening, how it is modulating the rainfall. So what happening in the 2020? So this is a very peculiar case. So in the 2020 year, what happened in the August month is received a very highest amount of rainfall. So, but there is no monsoon depressions. So only low pressures are there. So only the monsoon depressions are there. Only monsoon lows are there, and there is no depressions are formed in the 2020. Even though it is not formed, so it is received the highest amount of rainfall during the last 40 years. So in the season, so there are 12 low pressure seasons, low pressure areas are formed. Out of 12 low pressures, nearly 50% of the rain, 50% of the low pressures are formed in the only August itself. So that is a peculiar. The last this brings the heavy rainfall during the August when compared to this last 4 to 4 years. So this is the highest rainfall from the 1976 onwards. Next. So even though this you can see this is the climatology from the 1951 to 2000. So this is the A climatology, and B is the 2020 monsoon rainfall, and this is the departure. So even the central India is departure. So India as a whole has received the normal rainfall. So there is 109%. So slightly above this normal. So need to this excess rainfall. 110 is the excess rainfall. So we are receiving almost all 109% rainfall. Even though if you are receiving the central India, you can see this is a negative rainfall anomalies. You can see the in the central India. Why? Because this is a normal year. Because of this excess rainfall in the northeast, northwest region and the southern peninsula region, it has received a very high amount of rainfall. So because of these two regions, it is becoming normal. So why we are interested in this 2020? So even though it is a this region, so generally we will expect a normal monsoon years. Core region will be get normal heavy rainfall or most of the rainfall. So but in this case, so central India is dry. So what causes? So if you see the seasonal wise, you can see this. In the August, it received a very high amount of rainfall as a central India rainfall. So whereas you can see northwest and northwest and western Ghats region is a very high amount of rainfall compared to the climatology. Very high amount of rainfall has received. So this is brings this very curious. Why this monsoon? Then basically this monsoon rainfall basically produces by these monsoon depressions. Then we have looked into the depressions. Next slides. But if you see this monsoon depressions are decreasing. So you can see the climatology. So monsoon depressions are decreasing. So which contributed the most of rainfall? Then we looked into this 2020 monsoon. So in the June and July and August and September, you can see the August has received nearly 5 to 6 low pressure areas. So this is well marked low pressure areas, and none of this only the one cyclone is in the June. So other months it's not there. One or only one low pressure areas or two low pressure areas is there. So most of these regions this August received a more high amount of the low pressure, but none of them has intensified into a monsoon depressions. So that is this low pressure has contributed to rainfall. Okay, that why it is not intensified into a monsoon depressions. Then we have studied. Next slide. So because of this, you can see the evolution of the SST. So throughout the year, so this year shows this monsoon SST anomalies. So this is the April to April, May, June, July, August, and September. You can see most of the time. So these these SST anomalies, basin-wide warmings, we can see in the northern Indian Ocean. This basin-wide warming is continued persist in the all 4 months of the monsoon months. So you can see there's a very strong in July and August, the head Bay of Bengal. So there is a strong warming you can see in the head Arabian Sea, and the strong easterly winds are there. You can see this, the white arrow shows the strong easterly winds flow from this west north Pacific anticyclone. So this flow is extending here, and this is a convergence over the head of Arabian Sea. So this type of patterns we have seen in the August, but in the other months we are not able to see. So that's why it is a very peculiar case in the August. Next slide. So you can see this is the circulation in the August month. So this is the 1000 various levels. So we can see the near hectopascal 850 hectopascal levels. There is a clear the anticyclone one branch is coming, and which is matching with this cyclonic circulation over the Arabian Sea. So ahead of near to this Arabian Sea. So there is a strong, then one branch is coming, that is intensifying this in the circulation. So that is up to 500 hectopascals also you can see clearly. There is a strong vertical convection. So deep convection is there. So this promoted this rainfall over the northwest India and the Western Ghats region, and this leads to the central India deficit. So next slide. So this is the then we have to compare this why it is August 2020 is different. So then we have taken a highest amount of rainfall which has received this August. So from the 1979 to the recent period 2020. So this B and left panel, right panel shows this August composite, and this only August 2020 how the rainfall pattern. So you can see this in the northwest region and the Western Ghats region, high amount of rainfall we have found. So whereas this during the August time, so this central India region will receive this mostly the um, high amount of rainfall, and the Gujarat region will receive the very less amount of rainfall. But in the case of 2020, it has received very high amount of rainfall because of this cyclonic circulation very strong over the Arabian head of Arabian Sea. So this is the years we have taken this green circles. So this is the four events which are taken as a August composite, and this is the for the 2020. So we have taken. So next slide. So if you see that SST anomalies, how it is changing, even though if you August these years, so receiving the high amount of rainfall, so this August composite shows the signal of El Nino conditions, and the in Indian Ocean, this is a positive IOD conditions. Whereas in the August 2020, so this is weak La Nina condition, and this is basin-wide warming and very strong warming. You can see this pink color box. You can see very strong warming, which is absent in the August composite. So this peak warming has induced this low level circulation and low level convection. So this has contributed the normal rainfall over the Indian region, so and excess rainfall over the North-West and Western Ghats region. So this is a figure shows this SST anomalies, how it is changing. So you can see in the 2020 case, so the Nino 3.4 anomalies from the weak normal condition to it is becoming a La Nina conditions. That's what it is representing in a spatial pattern also. Whereas in the August composite, so these type of this is quite opposite. So it is showing this El Nino condition. This is showing the La Nina condition. So which is and basin-wide warming in the August 2020. So this has changed. Like you can see this not only this one. So Western North Pacific, this North Pacific also, you can see Western North Pacific is very warm. So warm anomalies you can see. Next slides. So then we have compared this how the August 2020 with the other high amount of rainfall. You can see the strong convergence is there, relative vorticity, strong vorticity is there, and this negative is the divergence. So divergence has over the Bay of Bengal has introduced to the head Bay of Bengal, whereas in the August composite, so you can see the strong convergence. So here also you can see convergence on the head Bay of Bengal, but the central bay, so you can see there's a negative divergence, negative vorticity. So this which which is causing this reduce this stability, and it is which is not allowing the monsoon depressions to grow the low pressure to the monsoon depressions. So and the pressure patterns also is very much different. You can see this is the August 2020. So western north is high pressure, and this is the low pressure in the head of Arabian Sea. So whereas this August composites, so this low pressure is not that type of pattern is not found. So whereas you can see this the pressure anomalies, you can see along the in the August composite along this monsoon trough region. So it is present the SST MS the sea level pressure anomalies, but here only the in the head Arabian Sea only that is positive anomalies of the pressure is there. So the temperatures are very high compared to the composites of the other years. So August 20 is very hot, and this induces the this mainly this Western North Pacific played a dominant role in modulating this August rainfall. Next slide. Yeah, so you can see this clearly. This stream function shows that because of this North Pacific, Western North Pacific, there is an anticyclone is there, and the cyclonic circulation which has intensified this circulation over the head Arabian Sea. So whereas in the August composites, you cannot see that much strength, and that is pattern also different. So the Western North Pacific is very high, and this anticyclone is there, whereas this the convergence is there. So this pattern difference also is there. And if you see, go for a higher level, so the strong convergence in the in the North Arabian Sea, and where is the composite, this is the divergence in the sea, so which is promoting, that means like this is very different than peculiar events. So convergence and divergence is also patterns also very much different, quite opposite to the composites and August 2020 cases. Next slide. Next slide. Yeah, thanks. So why these variations? So this pattern, you can see this because of this Western North Pacific, then flow is coming and intensifying these circulations. So then we have suspected this any Rossby this wave flux analysis, wave activity flux analysis we have done. So which is modulating in the these circulation patterns in the Indian region. So which is ultimately this causing the excess rainfall over Western Ghat region and Northwest India. So this Rossby waves, you can see this pattern. Next slide, you can see clearly. So yeah, this shows this meridional wind anomalies. So there is a this is the lower panel shows the composite of August, I'm not sure, but August 2020 it is different. So this is retrograde to this to up to extended this negative. Negative means northerly winds. That is strength. This is southerly. That the positive values are southerly. This is negative is northerly winds. So which is a strengthened this here, and it is extended up to the 5 degrees north, southern peninsular India. So whereas in the August composites, it is limited to up to 30 degrees north only. So whereas this in this case, it is retrogressed and it will include into the near to the equator. So which is strong and strong circulation patterns are changing in the 2020. So this induced this wave flux activity. So next slide, sir. Yeah, you can see this the positive correlation and negative correlations in this Indian region. So whereas this August 90s, this meridional wind anomalies, so this is like a cyclone patterns. So it is appearing. There is out of phase relation between the central India and the 200 hectopascal meridional. So these winds, this one is the positive correlation and is the negative correlations are there. They are out of phase. So which is very much different. So in the August cases. So next slide, sir. Yeah, this figure shows this wave activity flux in the August 2020 August composite SWOT. In the August 2020, there is strong convergence over this head of Arabian Sea and over this north of this one. And there is strong flow towards the Indian region. So whereas this composite side, so which is the higher latitudes, it is going towards this China. So it is not coming to the India. So this is the convergence and the divergence and is coming. So wave energy is coming. So which is causing this divergence or the strong divergence in the upper level. So which is promoting the low level convergence. So in this way, so August 2020 has received a very high amount of rainfall. Next slide. Yeah, you can see this Rossby wave. So generally the Rossby wave, this A, figure A, generally Rossby wave like this, it will be there. So in the August 2020, what will happen? Because of these changes, the flux, so which is included into this further towards the equator, so which is retrogressed and the pattern was changed. You can see the C. So Rossby wave has introduced up to reach near to the equator, nearly 5 degrees north. So which is causing this strong convergence over the north of Arabian Sea. So in this way, so India received a very high amount of rainfall in, during the August month, even though if it is a less monsoon depressions, and however this monsoon low pressure areas are there. So why these monsoon low pressures are not intensified? Because of this Western North Pacific is very strong, which is opposing the opposing this stability, barotropic instability. So that's why this is not intensified into the depressions. Yeah, next. So highlights of this talk. So ENSO and IM are teleconnections in the north and central India and the southern peninsula India. Rainfall is stronger and stable in all epochs. So you can see this in some epochs we have seen in the first. So these regions, north central India and the southern peninsular India. So the relation, if you see that between them, so it is very strong throughout the epochs. In some epochs, the central India and this some regions were shown the is weakening some epochs, and some epochs it is strong. So CMIPS analysis also we have done. So to show this how these variations, decadal variation of this monsoon, this climate drivers, how it is representing in the models. So most of the models is able to capture reasonably, but not very well. Some models are failed. So in the case of 2020, what will happen, because of this, most of the low pressures form because of this decrease in the baroclinic instability, so which is not promoting this the intensification of this low pressure into monsoon depressions. So then, and another cause is that because of the Rossby wave, so which is creating this and very intense low pressure over head of Arabian Sea, so which is causing this heavy rainfall in the western North-West India and Western Ghats regions. Next slide. Yeah, thank you. If you have any questions and comments, kindly let me know.
Thank you, Professor Nagaraju.
Thank you, sir.
Let me see that if there are any questions actually that has been put in the chat box. Just a minute.
Yeah.
I think there are no questions so far actually, because there is a lag between the talk and the YouTube. Maybe
Okay,
after that there'll be.
yeah,
So,
sure.
firstly, actually, that you had given a very interesting talk on a very important problem, and you highlighted about the case of the Indian summer monsoon of 2020, where that Barotropic Rossby Waves and the monsoon depressions actually.
Yeah.
So the presentation was very well organized. Actually, first of all, it was started with the basic fundamentals, and then you have gone a little bit deeper into the subject, and then you have shown the relationships. It was really interesting to see that. So in your presentation, you had made a starting with the definition of the monsoon, in which you covered about the land and ocean contrast, the temperature difference, and the driving mechanisms of the monsoons, like the differential temperature distribution between the land and the ocean, then the moist processes, the Earth's rotation, and the orographic effects. So how they actually govern the driving mechanisms of the monsoons. You have started with a very important pointers, like how these are the important factors that can influence the monsoon, progress of monsoon, and how it can impact the Indian region in form of rainfall. Also, you have mentioned a very interesting point in your slide, like about how the saturated soil basically behaves.
Yes, sir.
It behaves more like ocean than the land, actually. That was a very interesting statement to see that. And also you have actually highlighted upon the role of the moist processes, and several theories which are very significant for monsoon. Especially the 200 hectopascal streamlines that you have shown in January and July. This looks very interesting. Thereafter, actually, you touched upon the El Nino Southern Oscillations, which is again a very intense AC interaction phenomena. And you try to bring out a relationship between ENSO and the Indian summer monsoon, particularly emphasizing on the changes that you find in the Walker circulation and how it modulates the Indian summer monsoon rainfall. Some of the very significant things that I find in your presentation is very clearly mentioned about how this Walker circulation is basically getting weakening of this Walker circulation since the mid of the 19th century.
Yeah.
And how it has a relationship to the global warming. Because that's a very interesting thing to see that. And yeah, you have also made a composite of this Walker circulation from 5 degrees south, covering the area of 5 degrees south to 5 degrees north for 11 El Nino events, 1950 to 2002. And thereafter, you have actually touched upon how these positive IOD events basically evolves, and the Indian summer monsoon and its teleconnection, the different types of regional patterns that we get. It's very interesting to see that actually. And I think you mentioned about ENSO and the monsoon teleconnections are weakening. No, weakening in the
Yes, sir. Yes, weakening. But if you see the regional wise, so there is a changes. Some regions is getting
exactly.
significant.
Because what I find is that there are areas where there is a weakening and strengthening also trends over the Indian context. It's very interesting finding actually. And yeah, these are actually some of the general observations of the talk. It was a very interesting talk. I have noted down some few questions that I would like to some general questions that I have noted down.
Okay.
Okay, I think the questions are coming in the chat box. I will just go through that. So first, let me actually start the few questions that I have noted down. Because it is general in nature. Actually, some of the recent studies that we are doing here, it indicates that the ocean heat content in the Arabian Sea, especially in the Arabian Sea, is building up.
Yes, sir.
Is building up, and its warming trend is very clearly seen as compared to the Bay of Bengal.
Yes, sir.
So if you see these two semi-marginal basins like the Bay of Bengal, the Arabian Sea, the warming is more, the subsurface warming is more actually prominent over the Arabian Sea.
Yes, sir.
Now, now I'm very curious to know how this differential heating, subsurface heating, can have an impact on the summer monsoon, Indian summer monsoon.
I think in this case, like if it is a Arabian Sea is warming, then the gradient will be reduced. But in this case, what happening because of this West North Pacific, so which is extending through the Arabian Sea, so this circulation has intensified the this convergence over the Arabian Sea, sir. So that's why we are getting a very high amount of rainfall. So definitely these winds are pushing, like how the East Pacific and West Pacific is trade winds are pushing this warm water. So maybe these warm waters are pushing from this to the Arabian Sea. So there is no way to escape from there. So that's why maybe warming is happening in the Arabian Sea.
Okay, fine. And also there was a recent study which I had seen, because of course that study was directly linked with sea level rise and all.
Okay.
That was from IIT Pune.
Okay.
There is I was reading the paper in which it was mentioned about the strength of the Indian monsoon is weakening over time. The past
strength, yes, sir. We also find that one the overall the rainfall has decreasing. So because of this, mainly the temperature gradients only we are suspecting. So we are also not clear. So what causes this climate change? Maybe various factors. So we are seeing. So what causing this weakening of this rainfall? Primary suspect is this temperature gradients are weakening.
Okay. Fine. And also in the recent that I was watching the TV news, like there is a famine-like situation that is going to come up in Somalia, in Africa.
Okay.
It has been documented in the news also. So is there a teleconnection that is happening actually, which is creating this drought-like conditions there?
We have recently one paper I studied, sir, because of this mineral dust. So in the Arabian Sea, so it is acting as a elevated heat source, which is strengthening, and the most of the moisture is picking there in the Arabian Sea. So maybe that is the Somali coast, maybe drying, maybe that reason most of the moisture is sucking in the Arabian Sea.
Yes, absolutely. It is becoming very like it is a famine. They mentioned in the news it is going to be a famine-like situation. Yeah. And also in your presentation, you have shown about the GCMs, actually, the CMIP climate models.
Yes, climate models.
So according to your study, what could be the best performing GCMs for the Indian context? For the
that is very hard, difficult to tell. So some models we have found like MICRO 6 something, 2-3 models also we can say confidently. But that also is not maybe 60 to 70% only they have captured. So these people
This is for the rainfall, no? This is for the rainfall.
yeah.
But suppose the same models are compared for the sea surface temperature, SST. How do their correlation fit into actually? Are they the best performing? Yeah.
Yeah, SST also SST is okay, sir. So these almost all models are SST is okay, but except some models has a very large biases.
Yeah.
Yeah.
But actually, when this CMIP 6, which is the recent type of models have come out, earlier it was CMIP 5.
Yes, sir.
Now there are some models in CMIP 5, which is also there in CMIP 6 also.
Yes, sir.
So of course, the best performing model, as one of you mentioned, is Mirok 5 actually.
Yeah, yeah, 6.
So that was we had also done a study on that. We found it was good in CMIP 5 and consistently doing good in CMIP 6 also.
Yes, sir. Yeah.
Because we need to do a little bit more research into that areas actually. How to.
Yeah. Yes, sir.
Yeah. So these are my questions. I think it's a really interesting talk. And let me go to the chat box. There is a question actually from Kalyani.
Okay.
Kalyani Mantri Pragada. The question is model limitations, how far they may affect the study, and which model shows the better performance.
Yeah, already have. So according to my thing, like out of 29 models, we have found 2-3 models. Meroc 6 is performing best model. So this model effect will not affect because most of our study is based on the observations only, not based on the just we have verified the models.
Okay, thank you. I think this is the only question that I have seen in the chat box. There are no other questions.
Yeah, okay.
No other questions. So on behalf of the Ocean Society of India, I thank you for this wonderful talk. It was really very informative and a very, very important topic because, of course, our country is basically dependent on monsoon, actually. We need to know better about it, how it is behaving, what are the changes that is happening, and the rainfall patterns, especially the rainfall patterns. So thank you very much, Dr. Nagaraju. It was very enlightening and very interesting talk.
Yeah, thank you, sir. Thank you for giving opportunity to you and for Ocean Society of India also for organizers.
Yeah. I'm pretty sure actually that the participants must have benefited a lot because this is a very complex and a very interesting topic.
Yes, sir. Yeah.
Thank you very much.
Thank you,
Thank
sir.
you very much.
Can I leave, sir?
Yeah.
Yeah, okay,
I think we can log out now. Yeah.
Yes.
Thank you.
Okay. Thank you, sir.
So we will close then?
Yeah, we can close the meeting. Yeah.